Okay, so today we're going to start to learn about polar molecules. If we look at our learning goal for today, it says that I can predict the polarity of molecules based on their molecular shape and their electronegativity differences. So let's remember here that a covalent bond is the equal sharing of electrons between two nonmetals. Remember, if you have two nonmetals, you can't have any charges that bring them together because the charges on two nonmetals would both be negative. So we end up sharing electrons. So electrons are actually equally attracted to both nuclei. The equal electron density due to equal electronegativity. And the example that we have here is a hydrogen molecule. So hydrogen each have one electron. Okay, they end up getting shared. Okay, so if we were to draw sort of the electron density of this hydrogen molecule, we'd have two hydrogen nuclei in the middle. And the electrons could basically float anywhere around in that circle, which is sort of symbolistic of the overlapping s orbitals of hydrogen. Now, because one hydrogen is not more electronegative than the other, the electrons are going to be shared equally. When you have a difference in electronegativity, that's where you could get a polar molecule or a polar bond. So let's recap electronegativity and what it means. It describes how electrons are shared in a compound. And sometimes basically what you have is one atom within a molecule hogging the electrons more than the other. So let's consider the compound hydrochloric acid, HCl. The electron clouds here on your diagram in this little box here, they represent where two electrons in the hydrochloric acid bond spend their time. So you can see they're sort of more dark over on this side of the diagram than over here. Okay, that means that the electrons spend more of their time around the chlorine nucleus than around the hydrogen nucleus. Why is that? Okay, the shared electrons spend more time around chlorine than hydrogen. That means that chlorine's more electronegative than hydrogen, so it hogs those electrons more. That gives this side of the molecule a partially negative charge, and this side of the molecule a partially positive charge. Okay, so if we have a polar covalent bond, such as what I just showed you, that means you have an unequal sharing of electrons. So the electrons are still being shared, but one of the atoms is hogging the electrons more, and that's creating a partial charge. Okay, so in this case, chlorine is more electronegative than hydrogen, so it hogs the electrons more, and that gives you the partial charge on each atom. Now you have this funny little arrow thing shown here, okay? That basically shows you in which direction, what it does is you sort of draw the positive where the partial positive charge is, and then you draw an arrow in the direction of the negative charge. And it just basically symbolizes that that is a polar bond. All right, hopefully you remember this from grade 11. A bonding continuum. There is no sharp line between ionic and covalent bonding, okay? So you have a pure covalent bond over here where you have a zero difference in electronegativity, okay? As you increase the difference in electronegativity going this way, the bond becomes increasingly polar, and then eventually it's going to get so polar and those electrons are going to be hogged so much that atoms could actually grab them, get a full-on negative charge, and you end up with an ionic compound. Okay, a bond basically becomes ionic when the electronegativity difference between the two atoms goes above 1.7. Now some people ask, at what point does a bond go from being covalent to polar covalent? Usually the marker is at about, some textbooks will say about 0.4. Okay, so if you have an electronegativity difference between 0 and 0.4, you've got sort of a pure covalent bond, no unequal sharing, no partial charges. Anything above 0.4, you have some unequal sharing and you have those partial charges. All right, so a bond that you calculate to be polar may not be polar if the whole molecule is symmetrical, okay? So what we now have to consider is not just the bond between two atoms, but all the bonds within an entire molecule. So imagine a tug of war between atoms of the same strength around a central atom. The pull in one direction is the bond polarity or the bond dipole. The overall molecular polarity is known as the dipole moment, okay? So you have a dipole, or you can have a dipole within a bond. Okay, but you can also have a dipole within an entire molecule that's maybe consisting of 2 or 3 or 5 or 6 or however many bonds there are. If the pull is the same from all directions, then the electrons are not attracted to one atom over another, and the molecule is nonpolar. Now, I know that is a little bit confusing, so we're going to go through a bunch of examples to help you figure out what that last point means. All right, so we're going to do the first column here, and you guys are going to try the last 2 columns on your own. So the polarity in molecules. The Lewis structure of NH3, if you follow all your Lewis structure diagrams and your Vesper shapes and all that, you're going to know that ammonia has a Lewis structure that looks like that. This should be a delta sign, not a D. The difference in electronegativity of the bonds, you guys should be able to calculate that based on your periodic table. I'm going to take a look at it now. So nitrogen has an electronegativity of 3. Hydrogen has an electronegativity of 2.1, so when we subtract the 2, you get 1.9. Okay, so the bond polarity, that means that the nitrogen-hydrogen bond has a partially negative and a partially positive charge. Sorry, this should be 0.9. I can't subtract today. Okay, so if we're going to draw the bond dipole, you'll have the positive on this side pointing towards the negative. Now, the question is it a symmetrical molecule? Now, I have a slide to show you if it's a symmetrical molecule. In this case, it is not a symmetrical molecule. When you have an asymmetrical molecule and a polar bond, you will have molecular polarity, which basically just means that this area, you can kind of divide the molecule in half, such that this area is partially negative and that area is partially positive, and you end up with a big, huge molecular dipole that looks like that. So not only do you have bond polarity, you also have a dipole moment. So you try at home the ammonium ion and BrCl to see if you guys can figure out whether or not those molecules are polar. So again, just to recap, just because a molecule contains polar bonds does not necessarily mean that the molecule is polar. Both the shape of the molecule and the polarity of the bonds are necessary to determine if a molecule is nonpolar. In all symmetrical molecules, the sum of the bond dipoles is 0, and the molecule is always nonpolar. Bond dipoles basically get added together to produce a molecular dipole. If you have a non-zero molecular dipole, you have a polar molecule. So those are sort of your rules for molecular polarity. Couple more rules. It is important because it explains physical properties such as melting and boiling point. If you've got those partial charges, that's going to affect how well those molecules attract to each other and will therefore dictate the physical properties of that compound. So here are the 2 key sort of summary points that you need to know. Okay, and we're going to use these 2 rules to go through our examples. Molecules are polar if the bonds are polar, so you have partial charges on the bonds, and the molecule is not symmetrical. Here are your shapes of symmetrical molecules. Anything that's linear, trigonal planar, tetrahedral, trigonal bipyramidal, octahedral, and square planar, as long as all of the atoms bonded to the central atom are the same. So we're going to go through some molecules, some examples. Here is HF, hydrofluoric acid. It has a dipole moment, it has bond polarity. Fluorine is more electronegative than hydrogen, pulls it in that direction. Okay, it is a linear molecule, but you don't have the same atom on both sides. So if we divide the molecule in half, this half is partially negative, that half is partially positive. This is a polar molecule. It has a polar bond, and it's a polar molecule. Water, again, is polar. Why? Okay, within each of these bonds here, we've got oxygen pulling, okay, and being more electronegative. So you've got sort of a dipole going that way and a dipole going that way, okay? This one is the dipole moment for the entire molecule. So I'm just going to erase that just to make it a little bit more clear. So we have a shape. We've got polar bonds. That's one check. And we've got a shape that's non-symmetrical. We can divide the shape in half, get a partially negative side and a partially positive side. Therefore, we are polar. Ammonia, again, I went through this one. It's polar. Again, you need to be able to divide the molecule in half in such a way that you have a negative, partially negative charge on one side and partially positive, if I draw that down there, on the other side. So ammonia is also a polar molecule. I've already done that one. Carbon dioxide. In this case, our two bond dipoles end up basically canceling each other out. Okay, I can't draw a line that puts my partially negative and partially positive charges on one side and the other, okay? There's no way to divide this up such that I have a partially negative and a partially positive charge. So even though I have polar bonds, because my molecule is symmetrical, there's no net dipole, non-polar. Last example for today. Methane, again, says no net dipole. How come? Well, we do have some polar bonds here. The carbon-hydrogen bond is polar, okay, which makes your hydrogen, let me just double check this because there's a mistake on this slide. So your carbon's a little bit more electronegative, so it's actually delta negative, so if you can change that in your notes. And all the hydrogens are positive, okay? We have a symmetrical molecule, okay? And we have that central atom bonded to 4 of the same atoms. So that means that overall, this molecule has no polarity because, again, I cannot separate the partial positive and the partial negative charges. So that's it for today. Hopefully we'll clear up any misconceptions you have in class.